instruction, groups of instruction or program is given, this IC, it will work upon that instructions, group of instructions, or work upon the program, and it provides the result. Okay, that means we can say before that I want to tell you how it is manufactured. It is actually built according to the concept of very large scale integration or ultra large scale integration technology. That is different thing. You can learn about that technology in other by searching in Google actually. Okay. So this is the technology used to make this chip, and what it does, it actually takes instructions from the user, instructions or command from the user. What are the what function it has to perform? Okay, that depends upon the instruction given to the processor, microprocessor or CPU. Okay, that instruction gives by the user or the programmer. Okay, and also we require to provide data to the microprocessor also. Means suppose you want to perform addition operation using this microprocessor, what you have to do, you have to provide the instruction add to the microprocessor, and also you have to provide two datas. Which two datas you want to add, that data also need to be provided. So when you provide this data and instruction, it performs that intended operation, that addition operation, and provides the result as output. So this is actually one example of what it can perform, this 8085. So it can perform arithmetic, some arithmetic instructions, and some logical instructions also it can perform. So in together you can say it can perform wide variety of tasks that is actually under program control. When it can perform this in isolated device. Microprocessor as an isolated device cannot do anything. It should be connected with the other devices called peripherals. Okay. So at least it should be connected with an input device. Okay. For example, keyboard and output device, display unit where you can able to see the output. Also, you need to connect one memory device. Okay, where data can be stored. Okay, so microprocessor kit is shown here. You can see this is the microprocessor kit. An example of a microprocessor kit where microprocessor is connected. Okay, and memory devices, some other peripherals also connected. It has input unit. This is a keyboard, hexadecimal keyboard. It has actually hexadecimal keyboard, not ASCII keyboard, and it has the output devices, the 7-segment display. Okay, that you able to enter the instruction, whatever the operation you want to perform, addition or subtraction, anything, or any logical function, that should be given to this processor by using this hexadecimal keyboard, and we will able to see the result of the addition operation and other operations. Okay, in this output device, which is called 7-segment display. Clear? So this is the microprocessor, and we can say it's an isolated device cannot do anything. And this microprocessor is the heart of the microcomputer system. This is called a microcomputer system. Okay, this is called microcomputer system, and heart of the microcomputer system is the microprocessor. Okay. And but actually we'll go through the microcontroller later on. In microcontroller, memory and IO devices are already built into it. Inside the chip actually this is available. Here you are connecting the input device and output device externally, and memory also need to be connected. But in case of microcontroller, this memory and input device and output device all are there inside a single chip. Okay, this is the difference between the microprocessor and microcontroller. We'll later on go through the microcontroller in any other lecture. Okay, so today we'll go through this microprocessor and what is there inside this. See, we have talked about data. We are providing data to the microprocessor and also we are providing instruction. So there must be inside this CPU there must be some place, so where it can be kept. Okay, that means it has actually some registers. Okay, so register, REGISTERS, registers. These registers are nothing but actually group of flip flops. We have learned in digital electronics. So flip flops, one flip flop can store 1 bit of information. Okay, so if it is 8 bit, it can store 8 bit of information. Okay, or 1 byte of information. 8 bit is 1 byte, isn't it? Okay, and so this microprocessor has some registers where this data and the instruction can be kept before the processing of the data and according to the instruction. Okay, so there is a place for instruction also, there is a place for data. These are actually registers. Okay, we learn about these registers first. So one of the functional component of 8085 microprocessor or a CPU or any microprocessor or CPU, it should have some registers. So similar to we'll go through learning this in this topic, internal architecture of 8085 microprocessor, where we'll talk about what are the contents available inside, what are the functional components, you can say that available inside this chip. Okay, so internal architecture, we are seeing that. So microprocessor, so here you can see microprocessor, which is also called CPU, comes with wide variety of features and architectural capabilities nowadays actually, but all of them actually contain at least the following. These should be there. So when we talked about the register section, 8085 actually has register section. Okay, so this register section, that is some registers. Okay, so what type of registers are there, we have to learn again about this. So one part or one functional component is register section. Okay, and then another functional component is called ALU, arithmetic and logical unit. What is the function of this unit? To perform the addition. We have talked about addition. We are providing two data and we are providing the instruction add. Then where actually this addition will take place. So this operation will be performed by a hardware unit, a functional hardware unit available inside this microprocessor, that is called ALU. Okay, arithmetic and logical unit. So it is a hardware unit which can perform arithmetic and logical operations. And it has timing and control unit. It is the heart of the microprocessor, which is responsible for coordinating various activities within the microprocessor and also between the microprocessor and outside world. So general idea you can understand about this timing and control unit is to enable a particular register out of so many registers are there to perform a particular operation. Some registers need to be enabled. Okay, and when it need to be enabled and how the operation will take place to perform the addition operation. So that everything will controlled by a section. This is called timing and control. Okay. So this actually provides the clock. Okay. So also. So after applying a clock, output will be changed according to the input. So similar to that concept here also, we need to have a clock unit. We'll learn about this timing and control unit in details later on. So another section is there which is called interface section. Okay. So we've seen this 40 pins, 20 pins on the left side, 20 pins on the right side. These pins are used to connect with input device, output device, some peripherals, memory. Okay. So this is actually, these pins actually provides these lines, input and output communication lines, which can be used to connect this microprocessor to the outside world. Connect this microprocessor with the memory, keyboard, output device and input device. Also to provide the power supply to the microprocessor. Some pins are there, two pins are there for positive and ground power supply, two pins are there for connecting a crystal oscillator which can provide the clock. Okay. So this actually called in general interface section. We'll talk about this interface section again later on. So first we need to know about this C, that is all together shown here. What is inside a microprocessor or CPU? This is actually register section is there, ALU is there, timing and control unit is there, and interface section is there. This all together makes a CPU. Okay. So all CPU contains this. The 8085 has this. Okay. And this interface section provides communication lines, okay, to connect with the outside world. You can say to connect with the memory, keyboard, output device, input device, clock, power supply, etc. So this is in together called system bus. Okay. The bus means actually group of lines are called bus, group of communication lines. Okay. So this is called system interface section provides system bus. Okay. And we'll learn about this system bus later on and in detail. Okay. So whatever pins available in 8085, that pins are actually providing the system bus. Okay. So first we'll learn about this register section. Let's go through this register section first. Okay. Register section, we have actually in 8085 some registers are there which is actually according to their functions actually divided into two groups, actually classified as, you can say, registers accessible to the, some registers are there, the programmer or the user uses that registers to perform operations actually, or to perform to run the program. Okay. To run to execute the instructions. So datas are kept or instructions are kept, datas are kept in some registers. So these some registers are there which are actually accessible to the programmer. Programmer uses these registers to perform the operation. Okay. So these are called register accessible to the program, and some registers are actually internally used by the microprocessor itself for the internal operation, for their operation. Okay. And this is not accessible by the user or programmer, and which is called registers not accessible to the programmer. So this register section contains some registers which can be classified as register accessible to the programmer and registers not accessible to the programmer. And then we'll learn about this register accessible to the programmer. What type of registers are there? See, in registers accessible to the programmer, two types of registers are there which are called accessible to the programmer. One is called general purpose register, registers used for general purpose, and some special purpose registers are there. Okay. Some special functions are performed by using that register, that is called special purpose registers, and some general purpose registers are there. So we learn about these general purpose registers. Which general purpose registers are there? We can will have actually in 8085. These are the general purpose registers available. Okay, we have these 6 8-bit registers. Each register of size 8-bit with 8 flip-flops are there in a register. A register is there which is named as B, register B. Okay, which is actually registers are there. Okay, these are called 6 8-bit GPRs or general purpose registers. Okay, these are the function of these registers are actually general. We are using for general purpose, so it is called as general purpose registers. And these registers are 8-bit. We can use these registers as register pairs to store 16-bit data also. 16-bit data also. So, uh, which are uh, these register pairs B and C can be combined together to say PC register pair. D and E can be combined together to say, we can say register pair DE or HL register pair. Okay, these three groups can be made, and these are 16-bit. It becomes 16-bit. So we can use this register as a 8-bit registers. Also, it can be used as 16-bit registers. Okay. So these are used as 16-bit register to perform some 16-bit operations. So otherwise, it can perform 8-bit operation. That means that by looking into the register, we can say, by looking into this register, we can say this microprocessor can perform operation or arithmetic operation or data operation upon 8-bit data. Okay. So it's a 8-bit microprocessor. Okay. So we can perform 16-bit operations. We'll see how it can be performed. So it's a actually 8-bit processor because it's ALU also, arithmetical logical unit. Also Also, it is a 8-bit size. Okay, ALU can perform any arithmetic and logical operation upon 8-bit data at a time. Okay, it can take only 8-bit data at a time to perform the arithmetic or logical operation. Okay, so these registers are also given 8-bit registers. Okay, and this can be used as register pairs also. And some special purpose registers are there. We'll talk about these special purpose registers. Special purpose registers now. So one more register is there called 8-bit register is there called accumulator, which is also a 8-bit register like BCDEHL. It is also a 8-bit register, but it is a special purpose because whenever you perform any arithmetical logical operation upon 8-bit data, okay, one of the data you have to keep in accumulator, another data you can keep it in any register B, C, D, E or H. If you want to perform addition operation, one data must be there in accumulator. Okay. So, and after that you have to give the addition operation. Okay, addition instruction. Uh, So microprocessor will perform this addition with accumulator. One, it can take any general purpose register. It can take as A plus B. B is general purpose register. A is accumulator. Accumulator plus B. Accumulator plus C. Accumulator plus D. Accumulator plus H. Accumulator plus L. Any register. Okay. And also you can add accumulator plus accumulator. Okay. So and after the addition operation, important thing is after the addition operation, result will be stored in accumulator. Okay. So accumulator content will be modified after the addition operation, and it will contain the sum after the addition operation. Okay. So it's a 8-bit. You can say it's an 8-bit register used as a source of the data as well as destination of the data. So along with 6 8-bit GPRs, one 8-bit special purpose register called accumulator is available for the program. Okay. Most of the instruction execution is performed with accumulator. You are not saying all the instruction, most of the instruction, because uh, some instructions are available to perform operation upon 16-bit data, so that you cannot perform using accumulator because accumulator size is 8-bit. So all 8-bit operation can be done using accumulator. Okay, so most of the instruction execution is performed with accumulator and results are saved in accumulator. So here a example is written: addition up to 8-bit data can be performed by keeping one data essentially in accumulator. One data must be kept in accumulator, because you cannot we don't have actually instruction, or you cannot do B plus C. Okay, register B plus register C, this is not available. Okay, so one uh, register must be accumulator and another in any of the 6 available general purpose registers. Okay, so this is accumulator. And now we'll go through another register which is called program counter. So program counter is a 16-bit register, not 8-bit. Okay, it's a 16-bit register. Okay, so it actually contains the address of the instruction. So address of the instruction means you will learn actually. So instruction actually, or program or group of instructions, these are actually written in a memory. Okay, so using the input device, you have to write the program in a memory. You have to save the program in a memory, and memory has actually the memory locations. Okay, okay, from which memory location onwards you are keeping. It should have the location in order to identify where the program is written. Okay, so addresses are there, that is called memory location address. Okay, we'll discuss about this memory and memory address in another lecture. Okay, so here you need to know that this memory address of the memory which is connected with the 8085 microprocessor is 16 bit. Okay, each memory location is 16 bit. Okay, 16 address of the each memory location is 16 bit, and content of particular memory location is 8 bit. So data stored in a particular memory location is 8 bit, and memory location, that memory location address is 16 bit. Clear? So 8 bit location and 16-bit location can be written in hexadecimal. You can represent it in hexadecimal. 8-bit data are actually from, you can represent in hexadecimal as 00H. 00H means 10 means in binary it will be 0000, which can be written as 0H, and another 4 zeros 0000 can be again another 0H. It can be 00H. So 80000 in binary can be written as 00H or 01H, which is actually in binary 00000001. Okay, 02H, 03H. So this way you can write in hexadecimal or represent a data, 8-bit data in hexadecimal. So this is actually uh, way, actually ease way. Okay, so we can represent any binary data in hexadecimal in a very easy way. Okay, and without any confliction. Okay, that means 8-bit data can be represented using 2 hexadecimal digits, and it will vary from 00H to FFH in hexadecimal. F means 1111, another F is 1111. Total 8 1111 1111 in hexadecimal will be FFH. Okay, so these are the 8-bit data, and 16-bit data will be 0000H to FFH. Okay, these are 16-bit. Okay, so memory location actually starts from 0000H, and it actually can go up to FFFH. Okay, that means actually 64K. We'll talk about this memory and how memory size, everything in memory chapter. That will be talked in another video. Okay, so we have actually here you have to know what the program memory location. One example is here it actually given here. See, if the user stored a program memory location 2030H onwards, so this memory location onwards, a program is written. Okay, and that program should be written in incrementing order in a sequence. Okay, without skipping any memory location, because microprocessor will say to the microprocessor to execute from 2030H, will instruct this microprocessor. So it will start from here, it will go to 2030, then 2031, then 2032, then 2033, then 2034. This way it keep on going, okay, to execute the instructions or the program. So how the microprocessor or CPU is getting these locations? So actually this is the function of the program counter, which keeps the track of the memory location. When microprocessor is executing 2030, program counter content will be 2031. Okay, and then microprocessor get this 2031 from program counter, and it will execute from 2031, and at that time content of program counter becomes 2032. So program counter is automatically incremented by 1 always, okay, till the microprocessor encounters with the end instruction, okay, end the program. Okay, so microprocessor, see here what is written here, see, microprocessor is instructed to execute a program written from 2030H, then microprocessor loads 2030H in address bus. Now you need to understand this address bus. What is address bus? So this actually we talked about system bus in starting. System bus uh, contains, actually we can divide this system bus into three buses. One is called data bus, one is called address bus, another one is called control bus. We'll talk about this uh, later on about this bus, okay. But what we need to know in order to understand this program counter, microprocessor loads actually this data 2030H in address bus, and address bus is 16 bit. So if I've told about the address bus, actually addresses are from 0000 to FFFF. Actually these are actually 0000H means actually 16 bit, okay, 16 lines are there. So this is the address, and we are saying that is address bus of 16 bit size, okay. So 16 bit address bus. So this is actually used to identify a particular memory location in a memory. Okay. So when microprocessor goes to this memory location to start executing the program which is written from this location 2030H, the microprocessor saves actually 2031 in program counter. Okay. Content of program counter is 2031 next memory address, next 16 bit memory address, okay. So again then it will, from the program counter, 2031 will be loaded to into the address bus, and content of program counter becomes 2032. This way it will work. So this program counter keeps a track of the memory location, okay. So counter contents are loaded into the address bus, and program counter content is incremented by 1 to point next memory location, and so on. Okay. Program counter never keeps starting address of any program. Okay. So starting address is actually, here we have talked about 2030 onwards the program is written. So the user or the programmer is providing this 2030 this starting address to the microprocessor. So microprocessor directly loads this 2030 from the user onto the address bus, and first data saved into the program counter will be 20318. Okay. So this is the function of the program counter, and similar to the program counter, we have actually one another 16-bit register which is called stack pointer, which works upon the stack. Okay. So memory, whatever memory connected with the microprocessor, some part of the memory is used as stack. We'll learn about the stack later on. Okay. So upon this is the stack pointer, which is also 16-bit register, which gives the address of the stack, from which memory location onwards the memory is used as stack. That address is also a 16-bit address that is kept in a register called stack pointer. It gives the starting address of the stack. Okay. Yeah. So that is called stack pointer. We'll learn about the stack pointer in details later on. Okay. So here actually one example is given. Say uh, out of the total memory connected with the microprocessor, which I am saying from 0000H to FFFFH. So using 16-bit maximum possibility is this 0000H to FFFFH, which means actually 64 kilobytes. Okay. Mm. Means how many locations? 65 536 locations are there in the memory. Okay. So 65 536 is called as 64K. Okay. And byte means each location can store 1 byte of data. Okay. Or 8 bit of data. That's why it is called 64 kilobyte. Okay. The memory sizes. So in that memory, suppose you are using this particular memory location E0000 E000H to FFFFH. Want to use this memory location, total memory location, this total range as a stack. You can use this as a stack. So how you can use? We load actually uh, in stack pointers the last location FFFFH. Okay. This location will be stored onto the stack. So whenever you are uh, keeping a data, whenever you are entering a data, actually stack pointer is decremented by 1. Here you have seen program counter. In case of program counter, it is incremented by 1. Here stack pointer, so stack pointer must be the, you must keep the last location FFFFH, because each time a 8-bit data need to be stored, first the content of stack pointer is decremented by 1. Okay. First data, if the stack pointer content is FFFFH, so first it will be decremented, means FFFE it becomes, and first data will be stored onto that location. Okay. Clear? So this is called stack pointer operation. So first 8-bit data will be stored in FFFEH, then next FFFD, again decremented by 1 FFFD, and then again decremented by FFFC. Okay. So this way it will be decremented by 1 and a new data will be stored onto the stack. Okay. So how it works? Data actually to get back the data is returned back in last in first out, LIFO fashion. Okay. Whatever last in can be taken as first out. So first data in FFFFE, second data in FFFD, third data in FFFC. So if you want to get back the data, first data will come as actually content of FFFC, then FFFD, then FFFE. So last in, first out. Okay. So it works in LIFO fashion, stack. Okay. So this I've talked about stack pointer. This is another special purpose register. We're talking about special purpose registers now, and so you can go through. So this actually things, these notes will be provided as a link in the video. Okay, you can download these notes also in order to learn easily, okay, later on. So stack pointer, we talked about stack pointer. So what is the instruction use is written there. So we'll talk about this instruction later on. Okay, let's go to know about another register which is called flag register. Okay, flag register is another register which is also a special purpose register. Why it is called flag? So it actually shows the condition of the result. What is the condition of the result after any arithmetic and logical operation? Whenever the microprocessor is performing an arithmetic operation, say addition operation or logical and operation or anything, so if the result, condition of the result can be zero, okay, result can be negative, okay, result can contain carry. So these things actually are shown by a register called flag register. So it shows the condition of the result. So result will be stored in accumulator as you have seen, and the condition of result, whether result is we are getting uh, contains carry or result is zero or whatever, this condition is shown by a register called flag register. Okay, so here actually this is also 8-bit register, out of which actually 5 bits are only defined, 3 bits are not defined or not used. Okay, these 5 bits are defined are called, see, this is sign flag, whether the number is positive or negative. Okay, sign flag. Zero flag, whether the result is positive or negative. Sorry, zero or not zero. Auxiliary carry. So we'll learn about this auxiliary carry. I will tell you. Uh, then parity and then carry flag. So S actually stands for sign flag. Sign flag is actually will be set if D7 bit of the accumulator. Accumulator contains 8 bit. Result is 8 bit data which is stored in accumulator after the arithmetic and logical operation. So this 8 bit data can be named as D7 to D0. D7 is the MSB bit, most significant bit, and D0 is the LSB bit, least significant bit. Okay, D7, D6, D5, D4, D3, D2, D1, D7. These are the 8 bits. So out of this D7 bit, the sign flag is set if D7 bit of the accumulator is set. Means if it is 1 after the arithmetic and logical operation. So here actually we have assumed that results are stored in accumulator, which is the case actually in case of 8-bit operation. So flag register content is modified only when there is a 8-bit arithmetic and logical operation. And for 16-bit operation, microprocessor cannot use accumulator. Okay, that is the problem because accumulator size is 8-bit. Clear? So flag registers are actually modified after arithmetic and logical operation, and out of which the sign flag S will become this D7 bit will be of the flag register will be 1 if the MSB bit is 1. 1 means negative number, 0 means positive number. Okay. Then zero flag. So another flag is there. This next one, this D6 bit of the flag register. This is called zero flag. Okay, zero flag. This is set. This will be set means 1 when if the result of any arithmetical logical operation done by ALU is 0 after the logical arithmetic logical operation. Say 5 minus 5 operation is done. So after that you will get actually 0. If the data is suppose 0 1 H and you have decremented the content by 1, the data becomes 0 0 H. So in this case also the result is 0. So whenever the result is 0, whenever the content of accumulator becomes 0, this 0 flag will be set to 1. Okay, set means it becomes 1. So by looking into the 0 flag, we can able to know whether the result is 0 or not. Okay, if it is 1 means we come to know that we got the result as 0. Okay, clear? Similarly, we have auxiliary carry flag. auxiliary carry flag is the this flag is set when a carry is generated from bit D3 and passed to D4. So from uh, in accumulator, if D3 bit to D4 bit, there is a carry pass during the operation. If carry is generated in D3 bit during the addition operation of two 8-bit data, so D3 bit of first data and D3 bit of second data is added and it generated a carry which is transferred to D4 bit. Okay, carry will be added to the next bit. Okay, so when this happens actually, for this case only this flag will be set only from D3 to D4. So carry may be transferred from D0 to D1, D1 to D2. It can be possible that D5 to G6. These all are the possible uh, uh, are possible because of that depends upon the data. Okay, if both data are 1 1, then there will be a carry. Okay, if there is if D3 bit of the both data contains 0 0, so there will be no carry generated. So D3 to D4 there will be no carry transfer. Okay, so this is called this auxiliary carry. So if there is a carry transfer from D3 to D4, this flag will be set. Okay, this is called auxiliary carry flag. Now next we need to know about parity flag. So after the ALU, arithmetic and logical operation, okay, if the result has even number of ones, out of 8 bits, the number of bits as 1 is even. Okay, there are 2 ones or 4 ones or 6 ones or all bits are 1. Then parity flag will be set actually. Okay, otherwise it will be cleared. So for even number of this parity shows actually even parity. If parity is even, number of ones are even, parity flag will be set to 1. Okay, otherwise it will be cleared. Okay, so by looking into the parity flag we will be able to know how many ones are there in the result. Okay, clear. Similarly, we have this one D0 carry flag. This is called carry flag. So after the addition operation, if carry is generated, okay. So we have taken two 8-bit data that generated actually result is 16-bit. It generated a carry, okay. Say FF plus 01. If you add with FF 01, so FF becomes 00 with a carry 1, isn't it? So in case of this actually there will be a ninth bit which will be lost. Why it is lost? Sorry, this is lost because accumulator size is 8 bit. Ninth bit will be lost. Okay, but a flag, this flag will be set in order to show that carry is generated. So by looking into the carry flag, we will be able to know whether the result contains carry or not. Okay. So this is called carry flag. If the result is more than 8 bit, ninth bit is the carry generated, which is lost because of 8 bit size of the ALU and accumulator. Both are 8 bit. This condition of result is reflected as carry flag equal to 1. So carry flag becomes 1 in order to show a carry is generated which is lost. Okay. So this is called uh, flags. So we have talked about this all 5 flags. Okay. Out of 8 bit, these 5 flags are defined. Okay. And these are the 5 flags. So next we'll talk about, okay, let me show you. This is what you have gone through today. So these are actually, see, you can see here, accumulator 8 bit, flag registers 8, out of which 5 bits are defined. Then we have learned about these 6 general purpose register B, C, D, E, H, L, which can be combined together, BC as BC register pair, DE register pair, HL register pair. We have learned about program counter. This is actually 16 bit, it's written wrong here, 16 bit, and also this is stack pointer which is again 16 bit. Okay, here. So these are two these are two special purpose register. This one is also a special purpose register, and flag register is also a special purpose register. B, C, D, E, H, L are general purpose registers. Okay, so these are the total registers which are called as registers accessible to the program. Okay, and you have learned about general purpose register and accessible special purpose register. Okay. So register, one more section is there which is called register not accessible to the programmer. That will we will talk in next class. Thank you.